Hello! In this online lecture we will talk about statistics. I will give you some basic introduction to statistics. I will give you some intuition what statistics is and also what are the principles behind some most common tests like t-test. So first let's define statistics. So statistics is a branch of mathematics that focuses on organization, analysis and interpretations of a group of numbers. But what I like more, the definition, is that statistics is a method of pursuing truth. That if you have some hunch, then statistics is helping you to evaluate if those things can happen by chance or they are some part of patterns. So for example, if you inject rats with some drugs and you are looking at rats' behavior, then if you look at a group of rats, then you can evaluate with help of statistics if these changes in behaviors can be just happening by chance or they are rather unlikely to happen just by chance. Interestingly, word statistics comes from Italian word meaning state, and it was first developed for to help with taxation, to help to calculate how much taxes people have to pay. Okay, so first, if we have a set of numbers as here, just by looking at those numbers, it's difficult to get some good idea if there is any pattern or not. For that, it's good to, when analyzing some data, to organize those numbers in certain ways. One way, for example, is by creating distributions or frequency tables. So here is, for example, each of those numbers may indicate a level of stress as reported by different students. So you have multiple students reported the level of stress, and what you can do is that to get some better sense, to make better sense out of those numbers, you can count how many students reported stress rating 0, how many students reported stress level 1, 2, and so on. And now if you create such frequency tables, it is much easier to notice that the majority of students report stress level around 7. And now it is more clear that majority of students are rather stressed more than this level 5. But you can also divide your data in different bins. So here it was interval just by 1. Here you can group responses from 0 and 1 into one group, one category. Responses, students who are reporting level of stress 2 and 3 in second category, and so on. So now the binning of your frequency table is bigger, and now you can see results in even a simpler way. And also, as it's shown here, each of those frequencies can be easily represented by percent of people in given category. So how to get percent? So you are taking a number from given category, dividing it by total number of responses and multiplying it by 100%. But again, looking at multiple numbers is not as informative as looking at some plots. And this frequency tables which we created before can be now plotted in form of a histogram. So here on this axis you have frequency. It means how many people reported given level of stress. And here is stress rating. And you can see that this set of numbers, if plotted in form of histogram, is much more intuitively understood by people. But as we said, we can divide data in different intervals, and here it is interval of 2. So it is exactly the same data, but slightly differently divided. And when you plot histogram, you see that it is not exactly looking the same. It is rather more smooth version. So by having this bigger interval, the data is more smooth. All those details are lost or smeared. So it is something what has to be thought when you are creating histogram. What is the best binning? If the binning is too small, then there will be a lot of noise visible, a lot of fluctuations, which may not give you good pictures. Choosing too big interval, it will cause too much smoothing and losing some important information. So the choosing what is the binning for histograms is quite important for proper interpretations of data. So when we are doing some sampling in our experiments, when we are it's really important to have this large population size and also unbiased sampling. So for example, here is a pot with beans, and if we want to get some estimate what is the size of those beans, what is the distributions of sizes of those beans, one way is to take every single bean and measure its length, and later to plot it, and we will have excellent information what is the exact distributions of lengths. But what we will learn, what statistics is telling us, is that we don't need to measure all those beans, that if we take some sample from those beans, we can get quite good estimate what is the distributions of lengths of those beans. But the important thing is to get unbiased sample. So in this case, you will have to steer it well and take the spoon somewhere from the middle to get some hopefully random distribution of those beans. And now by looking at the lengths of only small number of beans, we can get some good approximations of lengths in entire pot. And it is similar with many experiments which we are doing. For example, you are familiar with pollings before different elections, and so usually you want to sample equally from all people who will be voting, but it is not easy. For example, you can imagine that taking random phone numbers from phone book, it would give you some good idea of those random sampling, but it's not really the case, because if you take those random numbers and you are calling those people during working hours, then probably you will only call people who are at home. So you will more likely to, for example, call housewives rather than people who are working somewhere in constructions without access to phone, for example. So sampling in unbiased way, it's not always easy, but it is important if we want to get this good estimate of our population. Another thing which we will talk about is normal distribution. So amazingly, a lot of things are distributed in this normal way. So if we are talking about length of beans, probably you will find that most of the beans have this around average this length, and the chance of getting very long beans or very small beans it will be decreasing according to this Gaussian distributions, that it will be quite likely to get beans with slightly different lengths, but it will be very unlikely to get this very tall or very short beans. And if you measure any other things, it will also go according to this Gaussian distributions. And in the second part, we will talk a little bit what is the reason for that. For now, I only wanted to introduce you to this distribution, which you probably know and heard about, that many statistics which are developed and you probably applied are based on assuming that data is distributed in this normal way, and it is a quite good assumption in many cases. And we will talk about this normal distribution in more details later. So actual data maybe not always distributed in this Gaussian way. They can be, there could be many different types of distributions. Here you see unimodal distributions with one peak. There could be approximately bimodal distributions, for example, with two peaks. Some approximately rectangular distributions with which doesn't have some clear peaks. And there could be many other types of distributions. One example of, for example, bimodal distribution is if you would, for example, measure what is the age of people in a toddler's play area. So definitely, probably you will find a lot of kids with a very small age. You will find some people around between 20 and 40, but they will be very unlikely to have probably some teenagers in this toddler's play area. On the other hand, if you would, for example, plot distributions of number of students across different grades, you will get this more or less rectangular distribution, because in each grade is approximately the same number of students. So here is just example that not all distributions are normal, and when applying statistics, it's really good to first look what is the distribution of your data to make sure that it is proper to apply certain statistical tests. Distribution, even if they are unimodal, they can be symmetrical or skewed in one or other way. Distribution, for example, one example of such skewed distribution, it could be, for example, number of children in a family. So here you see number of families, number of children. So most families have 0 or 1 kid, and very few families have 6 kids. So here again, you don't see this Gaussian distribution, you see this unimodal skewed distribution. Distribution can also be skewed in other way, and for example, if you look at if students would receive some relatively simple test, and you would look at percentage of correct answers, then you may find that most students answer this correctly, and few students will answer it incorrectly. So these distributions will be skewed toward this correct answers. When working with histograms and plotting data, it's important to know that the way how you plot it can be either informative or sometimes can be a little bit misleading. So one example of a little bit confusing plots is shown here, that here it is commission payments to travel agencies from different airlines across years, and you see that for this Delta Airlines these commissions are increasing over years, and it's similar for other airlines. But for the year 78, the commissions seems to be smaller, but it is because they are reporting here only the first half of year. So here what you can see is that the bin size is not equal, that here they are taking 1 year intervals, here is only half year interval. So without reading this fine print information that this is only half year, it may give this impressions that commission is decreasing. Also, often when you are making histograms, there is a question, should I plot it only portion of this which is changing? So here you see example of exactly the same histogram, but here it is plotted from 0, and here it is plotted from 1500,000 value. So here you can see it is zoom into this upper part, so you can see clear changes that in year 2006 there is the highest values, and those are values of mean house prices. So you can see that in this year 2000 those prices were higher than in following year. But if you look at this from 0, it seems like those changes may not be significant. So again, here it means it seems like this is very drastic differences, here not. So the way how you present data, it may give a different message. And which of those ways is better? Well, I would argue that it depends on variability, on error bars. If errors bars are very small, then those changes are highly significant, then I would say that showing this plot would be more meaningful to better in more detail see what is the error bars and how things are changing. If errors bars are big and those differences are not significant, then probably it's better to show it in this way, because it will better right away convey informations that there is small fluctuations, but those fluctuations in prices are not significant. So which of those plots to choose? I would argue it depends what are the variability and error bars. Okay, so when we are talking about distributions, here is another example of bimodal distribution. So there are two different distributions underlying, but not all distributions which have underlying different distributions will be this bimodal. So for example, if we measure what is the height of population of let's say students, we will find that if we measure what is the height of women, it is this distribution, height of men is this. So men on average are taller. So those are two different distributions, but if we plot what is the distributions of height regardless of gender, then we will see that it is unimodal distribution. So even that this is two different distributions are underlying it, the resulting distribution doesn't have to be bimodal. So how to characterize those different distributions? Usually people are using using most often what is the mean of distribution, but also when distributions are skewed, it's useful to calculate what is the median and mode. So mode, it is the value which is occurring the most often. Median, it is if you would sort all the values, then what is this middle value, and the mean is the average across all the observations. So here what you see is that each of those values, mean, median and mode, is plotted, and for distributions which is close to symmetric, all those three values are very similar. But for skewed distribution, the skewed distributions has the same median as the this distribution with solid line, but you can see that here values of mode and mean are quite different. And when values are highly skewed, or if they have some outliers, then probably median is better descriptions of these distributions than mean, because mean can be highly affected by some very high numbers. And here you have another examples where you have the skewed distributions, and when you calculate what is the mode, median and mean, you will get these different values. For many distributions which are symmetric or close to Gaussian, it really doesn't matter if you calculate mean, mode, or median. All those values will be very close to each other. So to give you some real-life example about difference between mean and median, here is some data from study showing what is the number of partners desired in next 30 years. And here is data collected from men and women. So they ask people how many sexual partners you desire in next 30 years. So most people seems to be desiring one sexual partner, but what you can find is that there is few men who desire between 100 and 1,000 partners, or between 1,000 and 10,000 partners. So there is very small number of men who wants this high number of partners. And if you would characterize this data just by mean, what you will find is that on average, men wants to have 64 sexual partners over next 30 years, while women want only 2.8. So you see this big difference in means between men and women, but again, this is those data for men are affected by those very few let's call it outliers. But if you look at distributions, you will find that for both genders, excluding those few men, that the data are quite similar. So this is again, if you want to have some sexy title for some newspaper, for some newspaper article, then you can report mean that men have this much higher desire. But if you are reporting some science article, then it is important to, in such case, it would be important to present this whole data and not only report mean, but also report median. And in this case, median is identical for both genders, and median probably is more reflecting what is this behavior in general population. Okay, so we said that distributions can be somehow defined by its mean or median or mode, but also the width of distribution is very important. So here you have example of two distributions, and one is narrower and other is broader. And again, mean is not one of the descriptions, but is not complete description. We also need to define what is the width, the distribution, the width of distribution, to get better idea about shape of this distribution. So how to calculate those things? So to calculate mean, as each of you know, it is just if we have observations, so here are some numbers, we are just summing up those observations and dividing by number of observations. So here the sigma, it means sum over all the observation, x, it is all those observations, and n is the number of samples, and m is the mean. Often mean is also denoted by this dash. So if you have some number with dash, usually it means that this is mean value of this x. So how to calculate width of the distribution? One of the ways is one of the measures is called variance, and here you are just from every observation you are subtracting mean, you are squaring it and summing up those squares of differences from mean and divided by number of observation. The other way to calculate width of distribution, which is related to variance, is standard deviation, and standard deviation is basically square root of variance. So as you know, the variance was described as the square, so standard deviation is just square root of this expression. So and SS here it means sum of squares, because here you are summing all those square differences. And here is a simple table showing exercise how to calculate the standard deviations by hand. So if you have some numbers, and in this example this number of dreams people had each night, so somebody has 7, 8, 8, 7, 3, 1 dream, and so the average number of dreams for this group, it was 6. So what you are doing is that from each of those numbers you are subtracting mean. So 7 minus 6 is 1, 3 minus 6 is minus 3, and so on, and you are taking square. So now you are discarding information about sign after squaring it, and summing up, and you are summing up all the squares and dividing it by n, by number of observation, and this is how you can calculate standard deviation. Okay, so why standard deviation is so often reported and important measure? Well, so for Gaussian distribution, standard deviation is describing, can be also interpreted what percentage of observations are falling in a given interval. So for example, if here is one standard deviation, then within plus minus standard deviation, around 64% of observations will fall. If we know what is the mean and we have some other distribution, then some Gaussian distribution, then we know that around 95% of observations will be falling between plus minus 2 standard deviation. So standard deviation is the nice way to, if you know what is the standard deviation, you also know what is the likelihood of seeing some observations bigger than this number or smaller than the standard deviation. And we will talk about it in following slides in more details. Okay, so we said that distributions can be defined by this mean and standard deviation, but even if we, there could be many different distributions which have exactly the same mean and exactly the same standard deviation, but they can have quite different shapes. So here you can see 4 examples of different distributions, and each of those distributions have exactly the same mean and mean 4 and unit standard deviation of 1. So here it is just to illustrate that in real data, mean and standard deviation is some approximation of distributions, but it does not provide exact description of distributions. That each of those distributions is different, and maybe those small differences matter. So it is only simplifications by describing distributions by mean and variance, but often it is quite useful simplification, and it provides quite good description of this distribution. So as I mentioned, standard deviation is a useful measure and of the width of distribution, and we can use this to convert numbers in any distribution to what is called z-score. So z-score, it is just telling us what is the number of standard deviation of the below or above mean of distribution. So if we have some distributions, and here could be some arbitrary numbers, then if we calculate mean, then any number which was one standard deviation unit from the mean, it will have z-score of 1. If something was one standard deviation below mean, it will have z-score of -1. So to give you some example, if you have some distributions of time spoken per hours by some kindergarten kids, you can see that the average was around 12. If they calculate standard deviation, it was 4 for this distribution. So now they can convert those numbers to z-score. So the average of 12, it will now have z-score of 0. And if something was below this mean, it will have negative z-score. Above the mean will have positive z-scores. And because standard deviation was 4, then kids which were, let's say, saying 16 words per hour, then they had the z-score of +1 and so on. And it may sound like a little bit useless exercise, but this measure is quite useful. For example, if you have many different scales and you want to put them and compare them next to each other. So for example, you measure what is the height of people, what is the age of people, and what is the weight of people. So each of those values, categories, will have quite different range. So distributions of heights, it will be, let's say, from 150 to 190 centimeters. But distribution of ages, if we talk about university students, it could be, let's say, between 18 to 50. So those are different scales. So by subtracting mean and calculating standard deviation, it is converting those different values into z-score. It will help to normalize and easier to compare next to each other, for example, heights and weight of students. And how to do this conversion? So the formula is very simple. If you have some observation, you are just subtracting mean and dividing by standard deviation, and now you are getting z-score. In MATLAB, you can use function called z-score. So here you can give number or vector of numbers, and it will calculate, if you give vector of numbers, it will calculate automatically what is the mean standard deviation, and it will return this values. So here you will have values of x converted to z-score. Here in the second output parameters, you will get what is the mean and what is the standard deviation. And here is example how to calculate here z-score. And if we know z-scores, we can also convert it back to original numbers. So any z-score multiplied by standard deviation plus mean, it will get us back original scores. So basically it is just z-score is convenient scaling, where we scale our data to have mean 0 and unit variance of 1. And in 10, 20 or in before that years ago, people were often using these tables, which were telling you, for example, if value has z-score of 1.6, what's the probability of seeing distribution of numbers above or below this value. So here it is z-score of 0.1, and there is around 4% of chance that there will be some observations between mean and the z-score, so it will be very narrow stripe here, and there will be almost 50% of chance of seeing something bigger than this z-score of 0.01. So this is what such tapes were used before, but now when we have computers and we are using MATLAB, there are functions which we can use, and in MATLAB functions to get us those information is norm CDF, so it is cumulative distribution functions. This from normal function, cumulative distribution, so it is from Gaussian function. And basically here we are specifying what is the mean of our distributions, what is the variance of our distribution, and also what is the at what point we want to evaluate it. So these functions will give us what percentage of numbers is smaller than this. If we want to know what percentage of numbers is bigger than this, we will just subtract it 1 from it. So all those curves distributions are assumed to be normalized to 1. So those points will tell you what's the percentage of points which will be smaller or bigger than this particular value for your distributions with this particular mean and with this particular standard deviation. So in this case, if it is distribution with 0 mean and unit standard deviation, so this is equivalent to asking, giving z-score and asking what percentage of numbers is smaller than this z-score. In statistics, we often assuming that things are significant if it can happen only at less than 5%, and this is often with assuming this normal distributions of our data. So for example, here it is distribution of happiness scores. So people were asked how happy they are, and it seems to be fitting quite well to normal distribution. And now what can be done is that, for example, if we want to know how if if we can ask people, for example, who won some lottery ticket, how happy they were 6 months later, and if their happiness was bigger than this, let's say 87, which is top 5%, then it would indicate that this is something what is unlikely to happen by chance. So it would indicate that this is by comparing this particular happiness score to this distribution, it would indicate that it's really this lottery winning probably had this effect on this increase happiness. When we are doing statistical tests, you will hear about one-tail and two-tail tests, and so what's the difference? For this test, what we were doing here, we were asking, is this person more happy than average? So here we are only focusing, is this person falling in this top 5%? But we can ask another question, is the level of happiness of this person different from general population? So here, either this person can be more happy or more unhappy than general population. So maybe winning lottery tickets and having so much money will cause some completely unexpected things happening in life, which may cause quite a distress. So maybe our hypothesis it should be not if this person is just more happy, but if happiness of this person is different from general population. In such case, the 5% it will be not be here, but it will be now we have to redistribute this 5% of significance, so it will be 2.5% on this end of distributions and 2.5% on this end of distribution. So if this person had this level of happiness, if our hypothesis was that he's more happy than general population, we would say yes, that's true. But if our hypothesis is this level of happiness different from general population, then the answer will be no, because he does not go to this top 2.5 or the bottom 2.5%. So depending how we define our hypothesis, our results may or may not be significant. Okay, so I made these introductions about different distributions because it's really important to look at your data to see what is the distributions of your data, because most of the statistical tests will assume that data is normal distributed, and if it is not normal distributed, then the results of your statistical test may be meaningless, may be incorrect. So now I will introduce you to what is the intuitions behind t-test. And t-test is assuming these Gaussian distributions, and we will get some examples why it is like that. So first, before I talk exactly about t-test, I will tell you about distribution of means. So if we have, for example, this uniform distribution, we can calculate distribution of means. And what is distribution of means? It means that if we take some sample of numbers from this distribution and calculate what is the mean. For example, if we take some 3 numbers from this distribution, and we will calculate what is the mean. So if those are those 3 numbers, then the mean will be slightly below 5. And we can repeat this process many times. So if we repeated this 50 times, it will be our distribution. So every time we calculate this mean from those three numbers, we will add it to this histogram. So if we repeat this process 1000 times, we will see that this distribution is starting looking a little bit like a normal distribution, this Gaussian distribution. And why it is like that? Well, there is only one chance, for example, to have a mean of 9 from three numbers. You will have to have three samples with exactly 9 to have mean 9. But there is many different combinations to get mean of 5, for example. That if you have 4, 5, and 6, it will be mean of 5. If you have 3, 5, 7, the mean will be 5, and so on. So because this is much more likely to get some average around the average of this distribution, these distributions of means will tend to have this normal shape. And one thing about this mean of this distributions of means is that we don't have to do this sampling by hand, that there is some formula which exactly tell us what will be the mean and the width of this resulting distribution. So the mean of this distribution of means, it will be always exactly as the mean of original distribution. So here it is that this mean of distribution of means, which is denoted by m, is exactly the same as mean of original distribution. And the standard deviation of this distribution, it will depend how many samples we are using to calculate the average. So here this we will calculate what is the standard deviation of original distribution, and in our example we were always using only 3 samples to calculate mean, so we will divide it by square root of 3, and it will tell us what is the standard deviation of the distributions of mean. Note that if we have many more samples, if we, for example, take calculate mean not from 3 but from 20 samples, then the standard deviation of this distribution of mean will be much smaller. And the standard deviation of this distribution of mean is also called standard error or standard error of mean. And as we increase number of samples, then these distributions will be getting more similar to normal distribution. Okay, so to summarize this, what I told you, if this is our original distribution, we can take some sample from this distribution, so it will be some sample which will be used to evaluate what is the original distribution, and when we calculate this distributions of means from this distribution, we will get this much more narrower distributions, and the width of this, the mean of these distributions will be the same as mean of this, and the width, it will be depending how many samples you will be using to calculate these distributions of means. And in a few slides, it will make more sense why to do this calculations, why it is good for. So here is example that we have some distribution of some numbers. So let's say that this is scores obtained on some computer game. So most people scored around 200, few people scored 300 or only 100. So let's say that those are distribution of scores in this computer game for general population. And now we will take some college students. Let's say that we will take 64 college students, and we will find that the average score for this 64 college students, it was 220. And the question is this distribution of students significantly different from general population? Are students really better, doing better in this game than general population? And to do it, what t-test is doing is that to compare this distribution from the 64 people to population, now it will we need to calculate these distributions of means. So from this general population, we will just choose by random 64 people. So we will choose by random those 64 people. We will calculate what is the average of scores for these 64 people, and we will plot this distribution. So we will take one set of 64 people, calculate what is the mean. We will take another set of 64 people, calculate what is the mean, and so on. And we will plot this distribution. So the most likely it will be that this mean of those 64 people from the general populations, it will be exactly as the mean of original distribution. And now from this, so notice that here we are calculating this distributions of means with the 64 samples. So we can do it analytically if we know what is the standard deviation of this. So now what we can do is that now if we have this distribution, what is the distributions of averages from the 64 people, we can see if those 64 students, if the average of those 64 students is where it falls in this distribution of means. So it turns out that it is very unlikely to choose from this normal distribution just by random some 64 people that they will have as big score as those students. So now by doing this distributions of means, we can say that the students perform statistically better than general population, because it is very unlikely, very low probability, below 5% probability, that randomly chosen 64 people from this population, the average will be as high as the average of students. And in MATLAB, if you have two populations and you would like to check if they means are significantly different, you can do this t-test. So it is t-test 2, where you're comparing two populations. So this is x and y. So x in this case, it could be this, let's say, 1,000 people sampled from the general population, and y it will be this 64 scores for the 64 students. And as an output, it will give you age. So it is if the hypothesis is true or false, so it will be either 0 or 1, and it will give you also p-value. So p-value, it will tell you how likely, how unlikely, what is this percent of in which percentile, how far to the tail of this distribution the mean of this sample is. So if the p-value is smaller than 0.05, it means that the chance of these distributions being below 5% it is bigger, that the chance is smaller than 5% for this to happen by chance. So in one point is that in many research papers, people are reporting not standard deviations, but the standard deviation of mean. So it is standard deviation divided by square root of number of observation. And based on what we spoke before, the rule of thumb is that if you see two bar plots, and here people are reporting what is this standard error, then the rule of thumb is that if those error bars do not overlap, then that the difference between those two bars is statistically different. But if those standard error bars do overlap, then probably those two groups are not statistically different. Okay, so this was quickly giving you intuition what the t-test is actually doing when you are performing, and as you see here, assuming this Gaussian distribution is important, that all those formulas are based on assuming this normal distribution. The other things which you may often hear in research papers is degree of freedom. So it is basically number of scores or observations -1. So it is in statistics it is number of free parameters which vary. And the last thing what I want to tell you during this first part of introductions to statistics is effect size. So not so much in neuroscience, but in psychology papers, you will find often results reported what is the difference between groups as effect size. So it is some measure which is has some good intuitive, it is easy to intuitively understood, and for that it's useful to report it, so people can get right away understand what is the difference between, how big is the difference between two populations. So the definition of this effect size is very simple. So if we have two distributions, we are just looking what is the mean of one distribution, subtracting what is the mean of the second distribution, and dividing by standard deviation. Here we are assuming when standard deviations for both distributions is the same. So effect size often denoted by D, it is difference between those two means divided by standard deviation. And as a rule of thumb, when the effect size is around 0.2, it is considered small, around 0.5 it is considered medium, and around 0.8 it's considered large, that this is quite big difference between both populations. Okay, so I will finish for now, and we will follow with part 2.